Hello people, we're going to continue discussing the reactions of alkynes, and in this case we're talking about oxidation of alkynes. Alright, so we're going to continue those reactions. Now today particularly we'll talk about ozonolysis of alkynes, and we have already studied ozonolysis of alkenes, okay, if you remember that. Alright, so that's slightly different. In ozonolysis of alkenes we get aldehydes or ketones depending upon the alkene we are starting with. Alright, but before we actually jump to ozonolysis of alkynes, I just want to give a quick revision of something that we have already studied, which is oxidation of alkynes using alkaline KMnO4 at low temperature. So pay attention what is happening here. So we just take some alkyne. Alright, so this is some alkyne we are taking, and we are going to oxidize it using alkaline KMnO4. Alright, and the temperature we are taking is a low temperature, so 298 to 303, something like that. Alright, so it's around 300 Kelvin we're gonna take, so that's about room temperature basically, and we oxidize this alkyne. We have already done that reaction, and what we do is this carbon, the one that is in the middle, gets oxidized to ketone, and the one that is terminal gets oxidized to carboxylic acid. What we get is dicarbonyl compound. And now with ozonolysis of alkyne, the reaction is pretty much same. The difference here would be that the terminal carbon does not get oxidized completely to carboxylic acid. It gets oxidized to aldehyde, because remember, ozone is a mild oxidizing agent, so the complete oxidation does not happen in this particular case. It's the partial oxidation. So we're gonna do that reaction with the same reactant with ozonolysis. So this happens in two steps, alright, and later on I'm going to explain the mechanism, and we're going to compare the mechanism with the alkene mechanism. It happens in two steps. One is we add ozone to it, and the second step is some sort of zinc and H2O. Now what we get here in this case is dicarbonyl compound, but instead of carboxylic acid we simply end up getting an aldehyde. So these two reactions are very similar to each other. The difference here is that the terminal carbon, if it is there, it stays as aldehyde. It does not get further oxidized to carboxylic acid. Now if I were to oxidize this compound using alkaline KMnO4, then I would get that carboxylic acid on the terminal carbon, right? If we did the ozonolysis of alkenes, so something like, alright, if we're doing that, CH3, C double bond OH plus formaldehyde. Okay, so these are the two aldehyde we get. So we basically break the bond here, adds double bond O. Alright, so basically breaking two bonds, and in this case we are breaking one pi bond and one sigma bond, form an intermediate. That intermediate is called as ozonoid, if you remember that. So that is the intermediate we are drawing here. Alright, and that is our ozonoid, and this then breaks up as this. Alright, so this portion is going to give you the aldehyde, and this portion is going to give you this aldehyde. Alright, that's how the breakup is happening. Now instead of let's say for example a double bond, we take a triple bond. So if you have ozonoid in this particular case, now instead of alkene, if you take an alkyne, so if I add a one more pi bond here, and so in that case I will have to keep up with the valency, I'll have to remove the hydrogens, one hydrogen from each of the carbon. Alright, so that is a triple bond now, and if I do the ozonolysis in this particular case, there are three bonds. Two bonds are going to break off, so one bond is going to stay as it is. This is the ozonoid derivative we get with alkyne. And now if you do the reduction using zinc, alright, so the two carbons are going to stay connected. One of the oxygen will have to remove. The two oxygens are going to get double bonded to the respective carbon, so we're gonna get this compound. This is basically a bicarbonyl compound, diketone or dialdehyde or aldehyde ketone, depending upon the type of alkyne you start with. Alright, so if you look at this product, this is very similar to the product we have already gotten here in this particular case, isn't it? So with alkaline KMnO4, the terminal carbon gets oxidized to carboxylic acid, and if you do the ozonolysis, it stays as aldehyde. And important to understand the distinction between these two reactions. Okay, let's take another example. We'll take ethine. Okay, simplest alkyne. If you take an ethine and do ozonolysis. Alright, so first is ozone, second one is ZnH2O. So you're basically removing 2 pi bonds from there, and you just add double bonded oxygen there, and you're done. Okay, so that is the product of ozonolysis. This is dialdehyde. Alright, if you start with something like butane and do the ozonolysis, so the same conditions here, remove the 2 pi bonds from the starting material. This is now diketone. So the reaction is very simple to understand. If it's an internal carbon, make a ketone. If it's a terminal carbon, make aldehyde. Okay, I hope you understood this. Okay, so the next reaction we're going to look at is the polymerization reaction of alkynes. Alkynes can also be used to make polymers. One of the most common polymer that we make is a neoprene rubber that is actually made from alkyne. And that is a linear polymer. So how is it made? So the first thing we do is we take acetylene, because that is the most common industrial chemical, and react it with cuprous chloride solution in presence of ammonium chloride, and we heat it. And what we get here is this compound. What we get here is a vinyl acetylene. In the next step, vinyl acetylene is reacted with HCl. We react with HCl. Now as soon as you do that, you should realize that there is a double and triple bond, so we should follow Markovnikov addition. So we are following Markovnikov addition, so we have to add HCl. Now where should we add? Basically, and as we know, the triple bonds are actually more reactive than the double bond, so the H should go to the triple bond. Now which carbon? The terminal carbon, because according to Markovnikov, hydrogen goes to the carbon that has more hydrogen. So remember, we are using selectivity here. Alright, so we have to select whether double or triple bond is getting attacked by HCl, and it is the triple bond because it is being more reactive. Alright, so let's do that. Alright, so after addition of HCl, we get this carbocation. So you get this carbocation, and that one, now the chlorine goes to that carbon. Obviously it is resonance stabilized, so you can have a resonance structure, and you can actually draw a resonance structure of that. So in fact these two carbocations are formed, and in that case you'll get 2 different products. Okay, so this is going to give you this product, alright, in which the chlorine is on the second carbon, and in another case you're gonna get this one, and this is basically the alene portion. And allenes are usually not very stable, so I don't believe that this product is actually formed as much. Okay, so we're going to eliminate that, all right, because of this alene portion. And this is a pretty neat, pretty stable compound. This is conjugated, there is a single double bond, so this is a conjugated compound, and this is called as chloroprene. Chloroprene is used in making neoprene rubber, which is very commonly used actually. Okay, I'll show you some diagrams here. All right, and so chloroprene is the unit of it basically. Okay, and if you polymerize it, okay, so let's say you have a bunch of these units and you polymerize them, and they are going to make bonds here, and as a result of that, the polymer we get is going to be this. So that is the neoprene. Understood? So that is what we get, neoprene. It's a very common rubber. Okay, so these are some of the uses of neoprene rubber. Laptop sleeves are actually made from it, bathing suits, boots, and even the surgical gloves can be made. These are what you call as non-latex gloves. They are made from it. So neoprene is actually quite useful. It's a very sturdy rubber. Neoprene rubber is a synthetic rubber, and it is used in making various different things. So just to review, to make neoprene, we start with acetylene, react it with cuprous chloride in ammonium chloride, heat it. What we get is a vinyl acetylene, and in vinyl acetylene we add HCl. According to Markovnikov's orientation, we get this carbocation, and from that we get chloroprene. You don't have to remember the second one, this particular carbocation, you don't have to remember that. This is the carbocation we get, and from that we get chloroprene. That is the more stable product, I believe. from chloroprene, this is how we make neoprene, and I also showed you the uses of neoprene. So the next type of polymer we're going to talk about is cyclic polymer that results from acetylene, alright, or alkyne. So let's say we take acetylene, and if this is heated in iron tube, Fe tube, red hot iron tube in fact, so you need to heat it very high temperature, and what happens is that acetylene gives you benzene. Now this is how it happens. Okay, you'll have to take 3 acetylene. All right, so we're taking 3 acetylene here. You heat it and they cyclize, and what you get is a benzene molecule. So this is something we get if you use acetylene and heat it in a iron tube. All right, you get benzene. Now if we were to take rather than this, let's add another group here. So instead of acetylene, if we take propyne, all right, then what is going to happen? And then in that case, obviously we'll have to we'll have to write it in this particular manner. All right, you have, this is a one propyne, this is another one, and this is the third propyne. I have to write a little crooked, but that should be fine. All right, and again the cyclization happen in the same manner, and you end up getting benzene ring where you have 1, 2, and 3 methyl group in alternating fashion. So you get this one. All right, and this is called as mesitylene. Okay, this is a mesitylene compound that we get. So similarly, some other derivatives can also be synthesized, but usually we don't discuss all of those reactions. These are the most important ones. All right, so this is basically the end of alkynes. Okay, so we have discussed physical chemical properties of alkynes. We have discussed the preparation, we have discussed the methods of preparation of alkynes, and we have discussed the reactions of alkynes. Okay, in the next session we will talk about aromatic hydrocarbons. All right, thank you.